So what I want to do today is finish pure state entanglement that we started last time, and talk a little bit about mixed state entanglement. I will not have time to say anything about multipartite pure state entanglement. Luckily, Matthias is doing just that, so you have that covered. So what we saw last time, I introduced two measures of entanglement. One is the distillable entanglement, and that's roughly how many EPR pairs we can get per copy of the state by LLC in the limit of large number of copies, right? Then there was another measure, the entanglement cost. What this was? This was the number of EPR pairs that we need to construct per copy to construct one copy of our state psi or rho in the general case, again in the asymptotic limits, right? And then introduced for pure states, right? This is like all bipartite. This measure, entropy of entanglement, which was very simple, right? Just the von Neumann entropy of the reduced density matrix. And I wrote this result that we start seeing why it was true, that all these quantities are the same, right? So that's the result. What I show you so far, I show you this last time, right? That the entanglement cost is always smaller than the entropy of entanglement. The protocol was very simple, right? What it was, well, basically Alice prepares locally the pure state, many copies of the pure state. She applies Schumacher compression to the B parts of the state, right? To just make it a small number of qubits, given roughly by n times entropy of the state, many qubits. She sends this through to Bob, and then they have a good approximation of the state by the properties of compression. How much entanglement they need for that? Well, they have to send by teleportation. So they use exactly right the entropy of entanglement per copy. Great. So this shows this. This I haven't shown you, but it's kind of natural, right? I just let you think about it. That the cost should always be equal, bigger or equal than the distillable entanglement. Why that should be? Well, suppose it was not, right? Then you could just generate as much entanglement as you want for free, right? So with one, you would first from one copy of your state, rho AB, you run distillable entanglement and get a number of EPR pairs. Then you run the cost process. But then, if distillable entanglement was bigger than entanglement cost, you would gain some entanglement, right? This process. And then you keep repeating and keep getting more and more EPR pairs, right? And that doesn't make sense, right? So there's more formal ways of showing that, but that's true. What I want to show you now to complete it is that also distillable entanglement is bigger or equal than entropy of entanglements, and therefore they all have to be the same, right? So let's show this. And I start telling you last time how to do it. So the idea is, because we don't have so much time, I will just give you the idea for 2 qubits, which I start doing, and then just let you figure out the general case of high dimensional systems. So suppose we have our quantum states. We can write in Chimby decomposition, right? And if it's a 2-qubit state, you can always write like this. Now again, we have a large number of copies, right? That was the rule of the game. And then we want to see how Alice and Bob, by local operations and class communication, can extract the largest numbers of copies of APR pair, right? So they go by LCC. So I'll show you how to transform by LCC this guy into a maximum entangled state of dimension D, okay? And then the yield, how much EPR pairs it can distill. Will be log D, right? That's the number of EPR pairs, right? Just think about it. I'll leave to you to think about it, right? But if you have a state of this form, that's right. This is one of the EPR pairs, the one we're using. If you take the L power of it, right, tensor power. That's exactly the case of this form, where D equals, right, 2 to the L. Okay, so just instead of thinking like these individual states, you take the tensor power. I just think about a big maximum entangled state, and we see how much we get of these guys by taking the log of the dimension here, right? So, but it's the same, right? Up to some maybe local change of base, which we can always do. Okay. So what is the idea? The idea is that Alice and Bob, they are perfectly correlated, right? Because of the Schmidt decomposition. So they are in the Schmidt decomposition base. So what Alice will do, she'll just measure the Hamming weight of her bit string, right? So she has this n bit in her register, and she just measures the Hamming weight. So Alice measures Hamming weight. So as you saw last time, that's the same thing. She could also, you can think that she's measuring the total sigma z, right? She just measures the total spin in the z direction. Okay, and now what happens? She'll get a particular Hamming weight. For example, she'll get that there are m1s in her string, but she'll have no idea about the position of it, right? And because it was initially everything superposition, now she'll get just a superposition over all possible strings with Hamming weight m, right? So that's the post-measurement state. So Alice gets, suppose she gets Hamming weight m. Then in that case, the post-measured states, what it is just a uniform superposition over all states with Hamming weight m on her side, but Bob is perfectly correlated, so it has the same, right? So you'll be just a state of the form exactly that one that I wrote, right? So it's a maximum entangled state, but now where I runs over all bit strings with Hamming weight m on her side, and the same for Bob. Now what is the value of D, right? D is equal to the number of strings, or maybe we should just call this like Dm. Dm. Number of strings Hamming weight m. And we saw how many strings we have. What is Dm? Yeah, right. So it's just n plus m. Right. So okay. So what will happen now? Just as last time, right? Because we have this independent copies, m will be sharply concentrated, right? So m will be sharply concentrated. So what should be m? M is the number of 1. M should be very close to p times n, right? And then this will allow us to tell us roughly, with very high probability to get a given number of a given d here, at least close range of values, and this will give the yield of the protocol in the end, right? So let's just calculate this a bit quickly because I want to go to big state. So we have n much bigger than 1 as before, and then what we can show is that the probability that m, what is the average of m? The average of m is n times p, right? That, right? So you can think of this, okay, it's in superposition, but just think about if you actually measure it, right? If you actually measure it, you just decohere, and then really just have a binomial distribution where with probability 1 minus p you have 0, with probability p you have 1, right? So it's a binomial distribution, it's very well behaved. It concentrates around the mean. So the probability that this is bigger than, for example, square root n will be exponentially small Yeah, square root n. So you have this kind of bound, right? Doesn't matter the numbers here. What matters to us is that with very high probability you get an m of other n times p up subleading corrections, right? But then that's good because we already computed, right? So what is a good approximation to this binomial number when you have n and n times p? Who remember? Exactly, right? So it's the exponential of the entropy of p, right? So these yields that are defined here, the number of EPR pairs that we get in the end, is the log, right? So it's roughly n HP, right? Great. So now we have a protocol that gives from n copies of psi output n times HP copies of EPR pairs. So this shows, right, that the distillable entanglement of the states is bigger than what is this HP? That's just the entropy of the reduced state on A or on B, right? Just think about it. If you trace out B here, you just get 1 qubit state with eigenvalues 1 minus P and P, right? Which is the entropy of entanglement, okay? So for 2 qubits, that's how it works, right? So, you can make it more precise, of course, just quantifying all the errors and the approximations, but that's the rough idea. So basically just measure the Hamming weights. So in information theory, that's also a type class. You measure the type of Alice strings because it's perfectly correlated with Bob. Whatever she gets, Bob will get the same. But because you only learn information about the weights, you have all this uniform superposition over the positions where the ones are, right? And this gives you the entanglement, right? And because of this I the limit, we have many copies of the same state. We have some concentration, and the yield gives exactly the entropy as we want. Okay. So that completes, right? So they are all the same, equal to the entropy of entanglements. For the general case, will be very similar, but now when you measure the Hamming weight, you measure something more complicated. You measure what is the total number of ones there, the total number of two there, the total number of threes in the state, right? And then you do something similar, and we work in the same way, so you can try to think about that. Okay, so that's what I want to say about few states. I'm going to start mixed states now, which we cover the rest of the talk. But is there any question first on this? Yes. Yeah, right. So that's what I mentioned last time, right? So think about this as they say in the Schmidt decomposition, right? They say can always and why we can always think that it's in Schmidt decomposition because we have local unitaries for free, right? So we can just rotate the basis to put in that form, right? Oh yes. Yeah. Right. So it's a good question. So for one copy, you can ask both questions. One is when you can deterministic expect the APR pair, and when you can probabilistically do so. There are criteria for both cases. Not for every state you can do that. There are some states that you cannot. But you can always we know the exact expression as well. So in the deterministic case, it's related to the theory of majorization. In the probabilistic case, then there's like a family of like entanglement measures. Like actually for the dimensional systems, there are d of them, and then if you just look at the mean of them over the two states, you tell the rate of conversion. But I won't have time to go into that. But it's also understood in one copy. But it's more complicated. It's not like a single function. You need many functions in that case. Yes. Yeah. Right. Because what is the Schmidt decomposition? For what? No, the Schmidt decomposition is the decomposition for every bipartite pure quantum space, right? It's nothing related to increased or not, right? So like it's just remember it's just a singular value decomposition for matrices, but right using this isomorphism, which is true for every bipartite pure state, right? Yes. Yeah, but it's just doesn't matter if it's critical or not, right? So you have your total many body system, whatever you want to do, as long as it's pure, right? If it is A and this is V, the entropy of A equals the entropy of V, right? Like that's independent of Hamilton or anything, right? It's just like a property of being a pure state, right? Overall. Um, okay. All right. So we can be pretty happy about this pure state bipartite, right? Because it's um, such a simple answer, right? So we can hope that okay, maybe in general it will be very simple and very nice. It turns out that it's not. It's much more complicated. So either if you go to multipartite states or if you go to mixed states, and I want to discuss the mixed states. So I want to discuss mixed bipartite entanglement here. I mean, on one hand, it's okay, it's bad news, more complicated. On the other hand, there's more opportunities, right, for work here, and there are many questions. There are more modern questions that uh, wasn't considered before. But even there's some very old question that has been open for like 20 years and relate very basic questions here that we do not know how to solve. I'll mention a few of them, but there are many open. So I want to just start with going back, right, to the first of the two questions that we were addressing for pure state entanglement. One is just this binary question: when is a density matrix rho B entangled, right? So when I gave you the definition last time, right? But the definition was what? That it's not entangled, it's separable if you can write rho B as a convex combination of product states, right? But that's not immediately useful because we have to test all these infinite many decompositions of the state, right? As convex combination of pure states, and see if for any one of them the pure states appear in there they are products or not, right? So that's very costly computationally, right? It's not something you can really do. And therefore, we would like to come up with better tests, right, to say if a state is entangled or not. And we know a few of them. Let me tell you one particular popular one, which is what we call the PPT test, which connects to this concept of a partial transposition. So PPT test. To introduce it, let me talk. Let me tell you what is a partial transposition or a partial transpose. So we all know what is the transpose of a matrix, right? The idea of the partial transpose is that we consider a bipartite operator, and we take the transpose, but only with respect to one of the subsystems, okay, and not with respect to the other one. And now you can ask how to do that, right? What is the definition? And the way to define it is to consider some operator on a bipartite vector space, right? A and B, and then just say, okay, we can always write any operator as a linear combination of tensor products of operator on A and operator on B, right? So we just write it as IJKL, some IJKL, cat I bra J for A, cat K bra L for B, right? We can write any operator that we want in this form. This is just some basis for A and B. And now we're going to, for this guy, suppose we want to take the partial transposition with respect to A. For a guy of this problem, we will know how to do, right? We take the partial the transpose here, and we do nothing here. And for a general operator, we just extend by linearity. Okay, so that's the way we do. So we're going to define. So it's important we fix a basis first. We fix local basis, and then we define the partial transpose with respect to A as just this operator. We do the transpose here, so now we get J and I. And we do nothing to B. Okay? That's how we define it. Now you can complain, well, this operation is basis dependent, right? It really depends the basis that we put here. If you put another local decomposition in terms of another local basis, it will change the operator. And that's true, it will change the operator, okay? But what does not change is the spectrum. So the spectrum, the eigenvalues of the partial transpose do not depend on the choice of base. Okay, and that's why that's a good operation. So you can show that all these different, is basis dependent the partial transposition, but if you change the basis, we get a different observable, a different operator, but it's related to the original one after local change of basis, right? So yes. Correct. That would this one is already not right, but here, I mean, I don't know actually. There is a reason, but I tell you the truth, I don't remember why we do the partial transposition. Like if you choose a real base, it would not matter, right? But I know that if you don't, it does matter and it's important transposition. But I'll have to tell you later. I don't know. I don't remember the reason. Anyway, okay. So yes. So if you had like continuous variables x and p, there will be, suppose you have x and then you have x and p for the A subsystem and x and p for the B subsystem, right? For like two electrons, for example, each one with position and moment. Then the interpretation of the partial transposition is that time reversal only on the A subsystem. So depends how you define it, but yeah, indeed, you invert the sign of momentum for the A particle. That's the way to think about it. Time reversal for one of the subsystems. Yes. If you do the transpose globally, the eigenvalues are the same, right? Yes. No. But so if you do the transpose of operator, the eigenvalues do not change, right? The eigenvalues are the same for any matrix in its transpose. No, even Hemitian, yeah. Okay, but why introducing this, right? It's just a mathematical definition. We're introducing it because of the following. Suppose rho AB is separable, okay? Then I claim that if you take the partial transposition over this guy, it's again a quantum state. In particular, it's positive stem definite. All the eigenvalues are equal or is bigger or equal than 0. Why? It's separable. Therefore, we can write as a convex combination of product states, right? Let's apply the partial transpose. That's the same as just getting the transpose of these guys, right? But these are density matrix, rho Ka. So the transpose is a density matrix again. So that's just a different separable state, but it's a separable state. In particular, it's a quantum state. So it's positive stem definite. Okay. Now the point is that that's not always true. Okay, there are some quantum states for which when we take the partial transposition, it gives negative eigenvalue. And if that's the case, we know for sure it's entangled, right? Because if you are separable, you have to give positive eigenvalue. Okay, so that's a test for entanglement. So if rho AB, let's denote the states, PPT is the set of all states with a positive partial transpose. If rho AB is not PPT, then we know for sure that it's entangled, right? So it's not separable. Right. In other words, if it's separable, it's PPT, what I showed you. But that's how we use it, right? So we just do this PPT test, we get a negative eigenvalue, say, oh, it's entangled. Great. So what's one example of a state that is detected here? A simple one. Let's just take our usual thing, rho AB will be the ZPR pair. This pi plus. Okay. What is the matrix representation of it? that's it, right? So that's just a 0, 0, cat 0, 0, brow 0, 0, cat 0, 0, brow 1, 1, cat 1, 1, brow 0, 0, cat 1, 1, brow 1, 1, right? But what if you take the partial transpose now? So what this will do is that you send these guys here to the middle. Okay, will not affect this guy, but this gets shifted here, right? So we change it to 0, 1 half, 0, 1 half. But now this is a block diagonal matrix. It has this outer block, which is positive, right? It's diagonal. But the inner block, there is 0 in the diagonals and there is half in the off diagonal, right? So the eigenvalue is a negative. So this has a negative eigenvalue. So it's not bigger or equal to 0, and therefore that's a test that is entangled, right? So of course for pure state we do not have to use that. We need, right? We know immediately if it's entangled or not. We just put in the Schmidt decomposition. But for mixed states that's useful, right? So that's the PPC test. Okay. Now, you can ask, is that a complete test, right? So does this detect all entangled states, right? So that's a natural question. And it turns out that, so that's the question, right? Is the set of PPC states the same as the set of separable states? And it turns out that that's the case for low-dimensional quantum systems. So for systems of 2 qubits, qubit and a qubit, or a qubit and a qubit, that's the case, okay? But in general, it's not. So in general, step is strictly contained in PPT for a system of 2 qubits and larger, okay? So that's like useful, you can test it, but it's not the complete answer, right? So you can test if you get that is not PPT, great, you know it's entangled. If you get that it's PPT, you do not know. And then you have to try something else, right? And I'll tell you later what you can try. So why that PPT is nice? Well, because it's easy to compute, right? So if you have a density matrix, you can just, you apply this partial transposition, you map some local base partial transposition, you compute eigenvalues, and then you have the answer, right? So that's much easier than just testing all possible decompositions of the states, right? But there is also another reason why this PPT test is very useful, and that's because it's related to distillability as well. Okay, so that's an interesting tool to study entanglement distillability for mixed states, and that's the connection I want to tell you now for a little bit. Yes. There is a specific example, but I didn't write it down. But I will. Maybe, let me do a side note about that. I don't know this example, but I know one interesting, which will require proof. But let me just tell you that like for large dimensions, that's the general case. Usually they say it will be PPC and it will be entangled at the same time. So in the following sense, suppose we have a quantum state on A, B, C now, and the CD for A and B, and then there is, think about C as the environment, okay, and that's the dimension. And now suppose we draw it from what we call Haar measure. So Haar measure is just a way of drawing quantum states at random. Okay, so it's just a uniform measure of the set of all pure quantum states. Right, so these pure quantum states, they are unit vectors. You can think as points in some hyper dimension, in some higher dimensional sphere, right? And we just have the uniform measure of this sphere. That's the Haar measure. Now we pick these states from the Haar measure. Then what we can show is that if this D, dimension of C, is in this range, 4 D squared and D to the cube, okay, so we choose in that way, then with high probability over the choice of psi, if we define rho B as the partial trace over C of psi, right? So you take the pure state and the partial trace C, you get a mixed state now. So now this induces a distribution over mixed states, D by D mixed state, right? So where this just maps like how noisy the state is, so kind of fix the amount of noise in the state. Then with very high probability, this rho is entangled. And it's PPC as well. Okay, and that's some is a result from a few years ago. So in some setting, that's the rule, right? It's not like exception. So this PPC test is quite weak in that sense to detect entanglement, right? But because what we're going to see now, this gives some interesting example of states with like interesting properties of entanglement. This is what we call bound entanglements, but we're going to see this now. 3 by 3, yeah, we know many examples, but just they don't have anything particular about them. That's why I don't remember them. So the way you construct that, you use another test for entanglement. For example, this thing is called entanglement weakness. So you get a 3 by 3 straight, you just construct an entanglement weakness, you prove that it's entangled, you complete the partial transposition, and it stays positive. So it's not so illuminating, I think, but yeah. Yes. Yeah, so that's a good point, right? Because the operator depends on the choice of basis, but its eigenvalues do not depend on the choice of basis, right? So because we only use the eigenvalues, that's independent of the choice of basis. Sorry? Exactly. Okay, so what is the connection with this syllable? Yeah, that's right. You would do that. Well, here, oh, sorry. When I mean PPT, I mean that rho AB is PPT. So, I mean that C is just to induce a measure on the mixed states, right? Think about C is just the purification of the mixed state. Uh, another thing, right? Because the partial transposition with respect to A is related to the partial transposition with respect to B up to a global transposition, right? And the global transposition does not change the eigenvalues. Doesn't matter if you choose A or B, you get the same result, right? For the eigenvalues. Yes. It's not. Yeah. Yeah. People have proposed it. What they do, they just say, okay, let's implement PPT, where PPT is not, but suppose you combine the joint action of PPT and then you add some global depolarizing noise, right? So you just mix the dense matrix maximally mixed state. And there is a way you can compute for the depolarization for which this composition is completely positive now. And then this you can implement. But it's usually the thresholds are not very good, so it's not really used in practice. But, okay, so let's remind what we mean by distillability, right? For quantum states, we say that rho AB, we call last time, is distillable if we have n copies of it for sufficiently a large n. We apply a LOTC operation, and then we should get a good approximation of the APR pair, right? Of a 2-qubit maximum entangled state. If you can do that, we say it's distillable, right? Of course, once we can do that, we care about rates as well, which is the distillable entanglement. We care about how many copies of this guy we can get per copy of this. But that's a more basic question, right? Can we get even one single copy or a good approximation of one single copy at all for arbitrary large n or not, right? And okay, why PPT is relevant for this question? A result that I'm going to show you now. Suppose rho AB is PPT. It could be separable, fine, but remember it can be entangled as well, but PPT. Then rho AB is not distillable, it's undistillable. Okay, meaning that doesn't matter how many copies you use here and which LOCC you use, you will not be able to get a good approximation of one EPR pair even, right? So okay, so that's a result we are going to see why. Follows just from the properties of the PPT operation. So it's a simple fact. But then suppose let's take an example of a row B, which is entangled, is not separable, but it's PPT. Right, so you have an interesting case where there is entanglement there, but this entanglement, for example, is not useful at all for teleportation, right? So we cannot extract EPR pair out of it, right? So even though we will need EPR pair to construct the state, right, because it's entangled, we cannot extract any EPR pair out. So this is what we call bound entanglement. So if you use our two measures that we defined last time, in this case, the entanglement cost will be positive, right? It needs entanglement to EPR pairs to construct the states, but the scalable entanglement is 0. Okay. Yes. You mean a particular example? Sure. Like let's just look back a very simple one. Okay, but let's just look back at that example that I wrote first time, where your quantum state is half a maximally entangled state, and with probability half, you have the maximally mixed states. So it's a qubit on A and a qubit on B, but on B you have like this label 2, right? Where this is like superposition of 0, 0 plus 1, 1, right? And I would like to extract a EPR pair out of it. So what is a LCC protocol that does that? It's a very simple one. You just make a local, Bob makes a local measurement on his system, right? So Bob measures projective measurement where one projector tells whether he's in this subspace, whether the other projector is just onto 2, 2. Okay? Now, Bob makes this measurement, and suppose he gets 2, 2. If he gets 2, 2, he collapses this guy out, he projects here, and then they say that they share maximum mix for Alice and 2 for Bob. So no entanglements, it failed. But now suppose they get this outcome, 0, 0, and 1, 1. Then it projects out this part, right? And they end up in a maximally entangled state. So this protocol is probabilistic, but with probability half, they get a maximally entangled state. Now, if they have many copies, they can just run over and over again, right? And the probability of failing goes to 0 exponential, right? So they can get a good approximation of EPR pair. So that's a very easy example. Of course, there are much more detailed, complex examples. I just gave you another one, which is for entanglement distillation of pure state, right? So what we do there, you have many copies of the pure state. You just measure, right, this Hamming weights, right? That would be the LCC protocol, right? You measure the Hamming weight and communicate what is the outcome that you get from Alice to Bob, right? So that's a more complicated LCC protocol, but there are even more. But it's that's it's always will be always of this form, right? So Alice makes a measurement, a smart measurement, communicates the outcome to Bob. Maybe Bob condition on that makes another measurement and back and forth, right? Until they are done. Okay, so you already see here a big difference of mixed state entanglement and pure state entanglement, right? So for pure state entanglement, these two quantities, they're always the same, right? So for mixed states, they can be qualitatively different, right? So like one can be non-zero while the other is 0, for example, right? So it's very different here. And in general, they'll be different, right? So it's very special cases where they are the same. Basically, when pretty much you have pure state entanglement in some form there. Okay. Yes. No, yeah. So the question was just an example of LCC protocol to distill entanglement. That's an example. Yeah, well, I don't have a specific one because I didn't write it down, and it wouldn't be too illuminated anyway. But in higher dimensions, in this case, most states will be bound entanglement, right? So let's go back to this example, right? So pick a pure state from the Haar measure, d by capital D. Choose capital D as this range, 4d squared and d to the cube. Trace out C to get a mixed state. So with very high probability, almost for every state with these parameters, it will be at the same time entangled and PPC. So these will all be bound entangled states right here. Okay. So why this is true? Let's see. Okay, so it's just like it's a very simple proof. It's because the partial transposition, it has a lot of nice properties. So one property is that it's stable under tensor. So suppose we have a system on A1, B1, and another one on A2, B2, and we take the partial transposition with respect to A, which means A1, A2 here, right? Then you can verify that's the same as the partial transposition with respect to A1 on the first density matrix, and the partial transposition with respect to A2 on the second density matrix. Okay, so that's one property. It's stable on the tensor, that will be useful. The second property is that it kind of commutes with LHC, with separate operations, and using what Matthias told before with this stochastic LHC even, right? So suppose we have, what is the stochastic LHC? That's just one of the cross operators of LHC, or in more general, of a separate operation, right? So it's M tensor N. And suppose we have some AB here. That's the output of like this stochastic LHC. And let's compute the partial transposition with respect to A of the output. Now, that's another property that you should check by yourself. But the point is that we can commute through the partial transposition to the inside. Okay, so that's the same as M star tensor N, the partial transposition of the partial transpose of rho A B with respect to A, M transpose and vector. Okay. So you change a little bit this lock, but it still is lock, right? So it's still, let me write in a better way. So that's still the same thing, right? So but now you just have to apply the complex conjugation. Okay. And the final property that we already saw is just that if you have a EPR pair, phi plus, for example, we do the partial transposition. It's not positive semi-definite, right? So if you look at the minimum eigenvalue here, that's smaller than 0, okay? And the claim now is that these three properties imply this thing, okay? So let's see what. Are they all clear what I mean? Any question? Okay. Yes. So is what we just saw there before, right? In the different notation. So we have the EPR pair, right? So is this density matrix is still written here? This one, right? We take the partial transposition, we get negative eigenvalue, right? So it has two eigenvalues equal to minus half, right? So this notation just means lambda mean. It just means the minimal eigenvalue of this operator, right? So I could even write here that's equal to minus half. Right? Okay. So, all right. So let's just take rho AB, which will be our PPC state, and let's just, actually let's do the other way. So suppose, let's show that if rho AB is distillable, it has to be NPC. It cannot be PPC. Okay. So suppose rho AB is distillable. You can distill entanglement. Then what happens? We have rho AB to the power of n. And what I mean, okay, because I was talking about everything deterministic, right? So let's just write a deterministic LHC, which we can always write in this form, right? As a separable operation. So this is the LHC operation. We know that the cross decomposition must have this product form, right? There are more restrictions, but we know at least that. And then by assumption, this will be equal to a state of 2 qubits, okay, which is up to some small error epsilon, the same as the EPR pair. where this epsilon can be as small as we want, right? That's the point of distillation, right? So we allow some approximation, but for every epsilon, we can get this good approximation, which gets closer and closer to 5 plus, perhaps going to a larger number of copies of n, right? But okay, but we should be able to do that. And now let's just take the partial transposition. So let's take the partial transposition here. It's the same as the partial transposition here, which after some error, and the partial transposition, it is a continuous function. So you can blow up the error actually as a function of the dimension of the state, but because it's a 2-qubit state here, it doesn't matter, right? So that's after some small error, the same as the partial transposition here, okay? But we know that this guy is not positive self-definite, right? This has an eigenvalue minus half. So this shows that this guy should not be positive self-definite, right? But let's see what this implies about the state rho AB. So we use our properties now, so we can commute through, use linearity of the partial transpose first. Then we use this second property, so we can write this as, get another chart. We can write this as nk star tensor nk right? We can put the partial transposition here on this guy by using property 2. But now let's use property 1. So by property 1, we can put here inside the tensor product, right? So that's the same as well as just have the partial transposition with respect to A to the power of n, right? But good. And we know that this operator has negative eigenvalues, right? By choosing epsilon sufficiently small, right? Such that this is approximation, right? Because one of the eigenvalues is minus half. If this epsilon sufficiently small, this guy would have to have negative eigenvalues as well, right? Okay, but very good. But now, what is this? This is lambda applied to rho AP CA. Oh, sorry. Where lambda is this following a completely positive map, right? So it's a separable map, a particular completely positive map. So what is the property of the completely positive map? If it's applied to a positive semi-definite state, it outputs a positive semi-definite state, right? But we know the output, it's not positive semi-definite, it has a negative eigenvalue. So the only way this can happen is if rho AB has negative eigenvalues, right? So this implies, this whole thing implies that has to be the case, okay? And therefore rho AB is not PPT. So we show that rho AB distillable implies rho AB is not PPT. The converse, if rho AB is PPT, it has to be undistillable, which is what I wrote there. Okay, so that's the proof. So it's very simple, very nice, right? It's just PPC is very special operation. It has all these nice properties, like which is it goes along very well with LCC, and it's like what we call stable under tensor. Right. Okay. So now one question, open question in entanglement theory, which I think is very nice, but I think it's hard because it's still open, despite many attempts by many people, is whether, is it the case that let's look at the set of all undistillable states, okay, every state we cannot distill a pair pair. Is this the same as PPT? We know that if it's PPT, it's undistillable. But is the converse true? Does every undistillable state has to be PPT? We do not know. And because distillability is a very important concept in entanglement theory, it tells us the usefulness of the state for teleportation, for example. that's a fundamental question, right? But it's a hard one. We don't know. So maybe one of you will solve it, right? That would be great. But you know, the fact that it's still open shows how special PPC is, right? So because you could think, maybe we just have to find another operation with the same three properties, right? Whenever we have a different operation with the same three properties, we could follow the same proof, and it would give maybe a different criterion for undecilability, which would be different from PPC. But we do not know any operation, right? So we do not know any operation with these three properties, right? So any other one, apart like things that are strictly weaker than PPT, right? So you know, it tells us there is something. Yeah, that this PPC it's a deep concept, right? Even though might not appear a priori, right? But this connection with scalability makes it important. Sorry, we do not have a proof that it doesn't exist either. It could be that it exists, but we don't know. Okay. Right. Let me see how I'm with time. Good. So let's now. I want to tell a little bit about entanglement measures for mixed states. Well, I already told you that, right? Cost and syllable entanglement, they can be very different now. But before that, let me just actually. Yeah, it should be okay. So let's go back to entanglement detection for a while. So we know, right, that PPT is a test for entanglement, but it's not complete, right? It's like, you know, you can easily implement it, but it's not complete. On the other hand, we know that for pure state, pure bipartite state, it's very easy to say if it's entangled or not, right? We just look at the rank of the reduced density matrix, and this tells. So the question is there a good way of telling if a density matrix rho AB is entangled or not in the general case, right? So is that something that you can do or not? And first, some bad news. Or is a result by Griffith? I'm not telling names of everyone actually, but okay, this is what's written here. So if you want to decide if a density matrix rho AB CD by CD, or actually given rho AB, suppose you want to decide if rho AB is separable, or if it's far away from separable, if the minimum over all separable states sigma of the trace knob difference that we saw last time is bigger than something like that goes like as a polynomial in the dimension of the states, right? So suppose basically this is roughly saying we want to tell if it's entangled or not with some accuracy 1 over poly z, right? With this error. Which of course, if instead of SEP we had PPT, we can solve this very easily, right? Because you can just compute eigenvalues, and that can do with very high accuracy. But we are promised that it's one of the two, and we have to decide which one it is. It's that the side is NP hard. Okay, so this is called separability problem sometimes. So this separability problem in general is a hard computational problem. Okay, so there won't be an easy solution like PPT test. So there won't be an easy criterion that you can just compute, you know, maybe with right in your maybe on a piece of paper, or even using your computer in an efficient way. Which means that won't be something simple as PPT. It will have to be something complicated. So this is an interesting way of comparing how entanglement for mixed state is much more complex than for pure state. There's a lot you could talk about. You could talk about what if it's constant accuracy. There are results, right? There are a lot of results in this direction, but I just want to tell you this one, just as a warning sign, right? That won't be a nice solution in general to this separability problem. Okay. Right. So, but then you can say, well, I still like to have one solution, right? And then let me tell you one way that you can always tell if it's entangled or not, like a hierarchy of tests that you can do. And the interesting point of it is that it features one fundamental aspect of entanglement, which is what we call monogamy of entanglement. Okay, and I don't know if you heard it before, but if you haven't, that's one of like the key features of entanglement. Right, so we like to say that entanglement is very different from classical correlation, right? It's a special kind of quantum correlation. One way to tell them apart is just to say, okay, entanglement are the correlations which cannot be freely shared, which are like monogamous in a sense. And this criterion that I introduced quantifies that very well. Okay, so the general thing would be monogamy. Entanglement. And the concept is one of a symmetric extension. So what is a symmetric extension? So we say that state sigma A B1 Bk is a density matrix on A and K B system is a K symmetric or a symmetric K extension of a density matrix rho AB if first rho AB is a reduction of sigma. So if you trace out all B's, B2, Bk, then we get a state on right rho AB1, and that should on AB1, and that should give rho. Okay, and at the same time, the state is symmetric if we permute the B copies. Okay, so if you just do this is like the swap operator, the swap between Bi, Bj, that changes right the two vector spaces. If you apply this to sigma, is a unitary, right? So we have to conjugate. We should get the same state. Okay. So what is the intuitive picture here? Is that we have an extension of the correlation of A and B, but now A is equally correlated to many copies of B, right? So each one of these B's, because they are symmetric, there is really, right? It's a you know, if you trace out any one of, if you trace out all but any one of them, it will give the same correlations of A with B. So what is a picture? So that's a picture. So we have A entangled with some B, right? But now actually this entanglement, if there is a K extension, you can think as this entanglement being equally shared by many people, right? And all these B's, they're the same, they're symmetric. Now the question is, can we always do that, right? For arbitrary K, can we always write any state of this form? And for classical correlations, the answer is yes, right? So, an arbitrary number of random variables can be as correlated as you want, right? So there's no restriction, right? The weather can be perfectly correlated with the stock market, right? With, I don't know, the arriving time of the bus. Usually they're not, but they could be, right? There's nothing preventing that. In quantum mechanics, it's different. Okay, so that's let's see how it works. Right, so just a name, if that happens, rho AB is K extendable. We give this name to it. Okay. So let's just do an observation, which is, this is what I said about classical correlations. is also true for separable states. So separable states, they are infinitely extendable. Why that's the case? Well, let's just take a separable state. Okay, that's a separable state, a general separable state. What is the k extension of these states? Who has a guess? So we want a big state, right? Which okay, also in this case it should be I. Who knows how to write an extension, k extension for this guy? Exactly, right? Yes. So you just that's an extension, right? That's a valid state, great. It's symmetric on the bits, so good. So that's the case, right? So we do. So maybe that's the picture. This is like the H, the set of all density matrices. Then we have the set of two extendable states. Then three extendable states, smaller, right? And then if it's extendable, they're separate, right? That's the same as. Okay. And now I have no idea about the size. Well, actually, it's having figured out. You can compute it, but it's not representative. But now why that's an interesting criteria? Because okay, that's like first that's a sequence of criteria now, right? For every k, you can just look for a k symmetric extension, and if you cannot find one, you know it's entangled, right? So it's kind of like a SDPBC test, but now when you increase k, the complexity increases, right? So note, numerically you can do that efficiently in dimension. That's what we call a semi-definite program, but right doesn't. If you don't know about it, it doesn't matter. But it's like numerically you can do this efficiently. You can check for a k extension efficiently in the dimension. If k is not too big, right? But of course, maybe k has to grow and grow. So an interesting result is that at least this test is complete. So rho AB is separable if and only if rho AB is k extendable for all k. Okay. So that's nice because this tells us really that we can right, a distinguishing feature of entanglements is correlations which cannot be freely shared, right? So if the state is entangled, if rho AB is entangled, maybe you can extend to a few copies of this B, but it has to stop at some point, right? So these correlations cannot be extended to an arbitrary number of B's, right? So for example, for an EPA pair, you cannot extend at all, right? Simply because any pure entangled states, there is not even a 2 extension. Okay, so that I leave as an exercise, right? It's easy to see, right? Because if there was, you trace out B2 and you get a mixed state on AB, right? On AB1, but it's a pure state. But it's a complete thing. So right. So now maybe related to your question, how many levels you have to go, right, to have a good approximation to step rule. We know answers to that too. That's still what like kind of is an interesting problem for research too. That there is more to be done here, more to understand. I'll tell you only one of the results. So this they go by the name. It's a family of results, but they go by the name of quantum definity theorems. And I don't want to explain the name. It's related to some classical result in probability distribution called definity theorem. And but I would just introduce a very particular case. But what you can show is that if rho AB is k extendable, Then it has to be close to a separable state in the following sense. If you take the minimum over all separable states of the trace norm of rho AB and sigma AB, this will be smaller than, I don't know if I got the constant right, but I think it's 4. 4 d squared over k, where rho AB is a density matrix on CD by CD. Okay. So you know the norm, the distance grows with dimension square, but it decreases with 1 over k, right? So if you want this to be like epsilon, you can just choose k, right? If there is a k extension, if there is a k extension where k equals to 4 d squared over epsilon, then they say this epsilon close, right? Then epsilon close to separable. Okay, so that allows us, right, in a sense, allows us to approximate the set of separable states, which, as I said, is very complicated, but a much nicer set, right, which is k extendable, but only approximately. But we have a control on the approximation, right? So you can ask whether you can improve this bound. It turns out that you cannot using trace norm. Then you can try to relax the norm, maybe some other norm, and then you can improve this bound. So there's all this research in this direction of understanding this quantitatively better. This connects to many other problems, like both in quantum information theory, also in computer science. This connects, like, there's an open problem called unique games conjecture. It's like a famous open problem in complexity theory, in the theory of approximation of algorithms that connected to it in a sense too. So although I will not tell you how, but it's to try to understand monogamy in a more quantitative way. I think the interesting problem is fundamental in quantum mechanics, is useful for entanglement detection, for example, like here, but it's also, I think, has a lot of interesting mathematics there. So if you're curious, you should check it out, but I don't have time to tell more about it. So I have like more 15 minutes. Graham said I could stop at, yeah. Well, I mean, if you go to the argument, I'll show you how you can actually construct this separate state out of the k extension. But just saying now, I think the best thing I can tell is just really because entanglement is monogamous, right? So it's really, the higher the k extension means the more you can share the correlations, right? And then the less entangled it can be. So it's really, is this connection of entanglement as this correlations which cannot be freely shared, right? It's monogamous correlation. More quantitatively, you have to go into the argument here, and I don't have time. But by the way, this is due to Matthias and friends. He's here. I forgot to mention. Yeah, it's like this cannot be smaller than order. That is like this omega. Okay, e over k. So yeah, this dimensional dependence is necessary if you have the one norm, the trace norm. Yes. Oh, monogamy is because, right? If you're in a monogamous relationship, right? The more monogamous relationship is, right? You can only be correlated with that person in your romantic relationship, at least romantic correlations. You understood? Yeah, here means the same. Here means that the more entangled, right? So you have A and you have B, one, and you have many Bs, right? They are like, potential partners for the entanglement of A, right? Monogamy of entanglement say that the more entangled A is with B, the less it can be with anyone else. Okay? So if they are in a masculine entangled state, they cannot be correlated at all with the rest. Now, if they are like in a weakly entangled state, then they can be correlated with more. But there is a limit on how many. And the only case that A can be equally correlated with an arbitrary number of P's is if there is no entanglement at all. If there is only classical correlation between A and each one of the P's. So, yes. Yeah, that's what I said. So you can do numerically on a computer using what is called a semi-definite program. So that's a class of convex optimization problems, which there is efficient solution, numerical solution, which runs as a low polynomial in the dimension of the matrix. Of course, the dimension of the matrix grows exponentially with k, right? So this method gives a runtime of order d to the power of k, right? So for small k, it's efficient, but of course, when k grows, it doesn't become efficient anymore. You can phrase like that if you want. Yeah. Yeah, that's why brute force cannot be a good approach, right? So you can do by brute force, but it takes exponential time in d in that case. Right? Yeah. But it's kind of saying that if you want to solve with this accuracy, you take exponential time in d, right? Because unless t equals n, which probably is not. Okay. More questions? All right. So the last thing I want to just mention briefly, how about entanglement measures for mixed states, right? Can we actually compute them? Can we compute the entanglement? We know the entanglement cost is not equal to the silver entanglement, but can we compute them, right? Or can we get bounds on them? What is our understanding? And again, it's not very good, our understanding. So, well, let me tell you what we know. Okay, so let me start with EC, the entanglement costs. And entanglement costs, we have some kind of expression, but as a limit. And I won't tell you how to get that, but I want to mention, because I want to mention an interesting open question as well in the entanglement field. So there is a measure that's called entanglement formation. I'm going to define now. If you compute the entanglement formation for n copies of rho AB, you divide by n and you take the limit. This gives the entanglement cost. Okay, so now what is the entanglement formation? That's kind of a natural way of getting a measure for mixed states from pure states. So all we do is just minimize over all ensembles, pure state ensembles, such that rho AB equals EI. This guy, okay? So it's just like pure state decomposition of rho AB, and we look at the average of the entanglement entropy. Right, so a mixed state has many decomposition as pure states, convex decomposition as pure states. Each one of them will have like a different average value of the entanglement entropy of the pure state. We look at the minimum one, and this gives entanglement formation. Yes. Yeah, but a mixed state you can always write as a convex combination of pure states, right? So you look over all possible decompositions as pure states, and you look at the one which minimizes this average entanglement. Okay. So this is not an easy thing to compute, but it's something you could try to compute, right? One copy. But even more so, you have to compute infinitely many copies. And there was a open question for many times, for many years. It's called like additivity conjecture, whether the limit was necessary or not. Okay, whether this was the case or not. It was like a famous question for a decade or so. Then in 2008, I think, so some time ago already, it was disproved. So we know the limit is needed, which makes it very hard to compute. But and this same additivity is connected to many other additivity questions in quantum information theory related to channel capacity and so on, which are also interesting. But the open question is that we understand very little this what is called non-additivity, meaning that this function is not additive. We understand very little about it. So we don't, the examples that we have, that there is a gap, is like random constructions actually, is a tiny gap. It's a really, really tiny gap. And we don't know whether they can vary, And if that's the case, if it's always a tiny gap, we do not care, right? So then that's already a good approximation, at least for entanglement cost. But if there is big gaps, we should care. So we not know that. So it's very interesting to try to understand better how big can this non-additivity be. But that seems also a hard problem. There isn't so much progress. But I think that's a problem that appears in entanglement theory and quantum information theory in general all the time. Like, we get expressions, but they involve limits. We do not understand limits, and we do not know how significant they are, right? How we can handle them in a good way. That's, I think, a challenge for future. All right. So the last thing I want to make then in just 5 minutes, I wanted to tell about the coupling a little bit, but we will not. The what? Yeah, because this quantity, right? That's the definition of the quantity. The name of the quantity is entanglement of formation. Because well, maybe because it connects to the entanglement cost, right? That's the entanglement related to the formation process of the state, right? Up to limits. Okay, so how about the syllable entanglement, right? Which is actually a more relevant quantity than the entanglement cost. Can we compute it? We cannot. We don't even have like a expression of this form for it. We know very little about it. Right, as in the dimension to you, we don't even know when it's 0 or not. Right, we don't have understanding when it's 0 or not. But we do have one bound, which I want to write. So this is called hashing bound. So we know that the syllable entanglement of rho AB is always bigger or equal to the entropy of rho B minus entropy of rho AB. Okay? And if you know that, that's the negative of the conditional entropy of A given B. Okay? Where? So what is the conditional entropy? That's a measure of how much information there is on A in addition to B, right? So suppose you have in the class case, you have two random variables. They are correlated. So if you know B, you know a little bit about A, of course, but they are correlated. The conditional entropy of A given B is how much new information there is on A on top of B. Right? And classically, this is always positive. But quantum, interesting, this can be negative, which then kind of, right, it's tricky how to make a operation interpretation. There is one called state merging. I don't have time to explain. But what is interesting is that this kind of weird examples, right, of states for which this is negative, this is exactly the entangled one. Or at least this gives a bound on how much API pairs you can extract from it. Right? So that's just a bound, but can be a useful bound, right? You can just get a state, compute this, and then at least you have a use for syllable entanglement there. You can compute and so on. But of course, we have examples where this is not a good bound, even though you can distill. So, we don't know much about it, right? So, we need more bounds. Both upper and lower bounds. So upper bounds, there is also an interesting story. There are ways of doing that. But we don't understand it very well, right? So now to connect with other things, really, what's another way to think about the syllable entanglement? It is, in a sense, it tells us about our ability to do quantum error correction, right? So for example, we want to distribute this entanglement over some noisy channel. We do it, and then it gets degraded, gets some big state, and now we want to revert it back to this good form, to this ideal form of PPFL. We can do teleportation. So right, to do that is some kind of quantum error correction. So our very limited understanding of this just shows how few we know about quantum error correction, right? So I think, as I mentioned at the beginning of the course, these kind of questions, they are not being as studied as they were like 10 or 15 years ago. So people have moved on, right? So they talk about all these applications. that I mentioned in condensed matter, in high energy physics, or Massis was saying about in algebraic complexity theory, in mathematics, computer science, and so on. That's great, but I think it's important, right? You have, I think this like core basic knowledge, which I just started giving here. That I will need more lectures, right, to give the whole basis. But I think that's important to know, right? Because then that gives the basis for these applications, and eventually, hopefully, we make progress on these core problems again as well, right? So, and maybe you do it. So I hope I convince you it's an interesting area. Even though it's already old, these basics, there's too many open problems, and we need new ideas. So that's all. I'll stop here. Thank you. Any final question? Yes. No, entanglement formation to calculate it with epsilon, that's NP hard. You can show that. Yes. Yes. Indeed. So for the one-way channel capacity, if the channel is like too extendable, there is a similar notion for the channel, then zero capacity. Then there is zero capacity, right? Because the environment will get the same information as the output, right? So yeah. Yes. Sure. Right. Yeah, sometimes people look at that. So like total quantum correlations, they look using mutual information, and class correlations, they look when they measure locally the system, and they look at the classical mutual information. And then the difference is what they call sometimes quantum discord, which would be like the difference of the quantum and the classical correlation. So some people study this and try to see the difference. Okay. So, oh yes. Yeah. Right. It depends. So if quantum correlations you mean entanglement, then we have to look at some measure of entanglement and see how much entanglement there is there, right? And for class correlations, you could look. Then it really depends on your definition of class correlation, right? So a classical, yeah. So but some people study that in this context of discord. So for them, they consider class correlations that you can attain by measuring locally the quantum system. So you can measure locally and look at this correlation, whatever way you want, using music information, and then you can compare with, right, whatever measure of correlation using the quantum system, and you can see gaps and so on. But it's not like a clear-cut question because